Hello everyone, myself Mr. Narsimharao, Assistant Professor of Physics in the Department of H&S in Pace Institute of Technology and Sciences, Autonomous. So let's discuss about ferromagnetism and its behavior, that is hysteresis. Ferromagnetism and hysteresis. What are the ferromagnetic materials? First of all, this is the one of the class of magnetic materials. Basically, magnetic materials are classified into 5 categories: diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. So out of these 5 categories, the ferromagnetic materials are very important. Now, what is ferromagnetic material? If it is the ferromagnetic material, in this ferromagnetic materials, each atom or molecule is acquired by magnetic moment. It has a direction. All these atomic magnetic dipoles are aligned in the same direction, parallel to each other in this way. In this way, atomic dipoles are aligned parallel to each other. Then the resultant magnetic moment is not equal to 0. It has certain value. That resultant magnetic moment and it has resultant magnetism, that is called spontaneous magnetization. What is that? Spontaneous magnetization. Now, this spontaneous magnetization is influenced by the temperature of the ferromagnetic material. That is explained by the scientist Curie-Weiss. There is a Curie-Weiss law. According to that Curie-Weiss law, the susceptibility of the ferromagnetic material varies with respect to temperature, as the susceptibility is equal to C by T minus Tc. Here C is the Curie constant. Tc is the Curie temperature. So in this way, the magnetic property of the ferromagnetic material varies with respect to temperature. Now, this ferromagnetic materials has a certain specific behavior, that is hysteresis. That is hysteresis. Let us see what is hysteresis of the ferromagnetic materials. Hysteresis. So what is hysteresis first of all? So hysteresis means the magnetic flux density within the ferromagnetic material is lag behind the applied magnetic field intensity. That means if you apply the magnetic field to a ferromagnetic material, the ferromagnetic material is acquired certain magnetism that is understood in terms of magnetic moment or magnetic flux density. If we explain in terms of magnetic flux density, that magnetic flux density lags behind applied magnetic field intensity. Let me explain this applied magnetic field intensity with respect to applied field. Now, take a graph, that is, take applied magnetic field intensity on x-axis and magnetic flux density in the ferromagnetic material is taking on y-axis. Now, we are taking ferromagnetic materials, ferromagnetic materials. So it has certain spontaneous magnetization with respect to if the temperature is applied, then the ferromagnetism doesn't have spontaneous magnetization. Now, if the applied magnetic field intensity is 0, then spontaneous magnetization is 0. Spontaneous magnetization is 0. If we increase the applied magnetic field intensity, that means if it is a ferromagnetic material, we are applying a magnetic field like this. The magnetic material is magnetized, and how much it is magnetized we are discussing in terms of magnetic flux density within the magnetic material. Now take a graph. We are increasing the applied magnetic field intensity, then the magnetic flux density within the ferromagnetic material also increases, but it does not increases linearly, it increases non-linearly like this. It increases non-linearly. After crossing certain applied magnetic field intensity, the magnetic flux density remains constant, it does not increases. That state of the ferromagnetic material is called saturation state. This is the saturation state. Now decrease the strength intensity of the applied magnetic field, then the magnetic flux density within the ferromagnetic material also decreases, in this way, but it does not retrace its original path. It decreases like this, it decreases like this. So here the applied magnetic field at this point, the applied magnetic field intensity is 0, but the magnetic flux density within the ferromagnetic material does not comes to 0. There exists certain magnetic flux density within the ferromagnetic material. That magnetic flux density, okay, is called residual flux density. What is that? Residual flux density indicated by Br, residual flux density. This property of the ferromagnetic material, property means it is there is a magnetic flux density remains within the ferromagnetic material even though the applied magnetic field intensity is 0. That property of the ferromagnetic material is called retentivity. What is that? Retentivity. Retentivity. Now, here there is certain magnetic flux density within the ferromagnetic material. The applied magnetic field H is equal applied magnetic field. Now, let us see what happens if you apply a magnetic field in the reverse direction to the ferromagnetic material. Here at this point, the magnetic field applied is 0, but there exists residual magnetic flux density. Now apply the magnetic field in the reverse direction. What happens? Reverse direction means the magnetic field is applying in this direction and increase. Let us see what happens in the ferromagnetic material. So in this graph, applied magnetic field intensity increases in reverse direction, then the magnetic flux density within the ferromagnetic material decreases. This value Br, this value decreases and becomes 0 and becomes 0. at a particular applied magnetic field intensity. That particular applied magnetic field intensity is called coercive field. That is called coercive field, HC. So what is coercive field in the ferromagnetic material in case of hysteresis behavior? The coercive field is defined as the applied magnetic field intensity at which the residual magnetic flux density becomes zero, and this property of the ferromagnetic material is called coercivity. What is that? Coercivity. Coercivity. Now, what happens after crossing applied field HC? Now, applied field is increasing in the reverse direction greater than HC. Then the material magnetized in the reverse direction. That means initially in this direction it is magnetized, and after that it is magnetized in opposite direction. That means magnetic flux density increases in the negative direction. So it reaches a saturation state in this case also. After reaching the saturation state, if we decrease the applied magnetic field intensity, then the magnetic flux density also decreases. In this way, there is a magnetic flux density within the ferromagnetic material, even though the applied magnetic field intensity is zero. After that, if we increase the applied magnetic field intensity in the positive direction, then the magnetic flux density decreases and becomes zero. And if you increase the magnetic field intensity, then it is magnetized in the positive direction as initial, like this. So this is the hysteresis behavior of the ferromagnetic materials. So here there are four important terms. They are residual flux density, retentivity, coercive field, and coercivity. Residual flux density is defined as the magnetic flux density within the ferromagnetic material, even though the applied magnetic field intensity is zero. Retentivity, it is the property of the ferromagnetic material. There is a certain magnetic flux density retained by the ferromagnetic material, even though the applied magnetic field intensity is zero. Next, coercive field. It is the reverse applied magnetic field intensity for which the residual flux density becomes zero. Coercivity. It is a property of the ferromagnetic material in this hysteresis case. That is, the residual flux density becomes zero for a particular applied magnetic field. Now, this is a cyclic process. What is this? This is a cyclic process. Cyclic process. In this cyclic process, there is a certain amount of energy wasted in the form of heat in the ferromagnetic material. That wasted energy is loss of energy in the ferromagnetic material. That loss of energy is called hysteresis loss. What is that? Hysteresis loss. Hysteresis Loss. What is hysteresis loss? There is a loss of energy in the ferromagnetic material during the cyclic process of the hysteresis behavior. That loss of energy is called hysteresis loss. This hysteresis loss is exactly equal to the area of the loop. Hysteresis loss is equal to area of the hysteresis loop. Hysteresis loss is equal to area of loop. Now, based on this hysteresis loss, that means hysteresis loop area, the ferromagnetic materials are classified into two categories. They are soft magnetic materials and hard magnetic materials. What is that? Soft magnetic materials and hard magnetic materials. Hard magnetic materials. What is soft magnetic material? The hysteresis loss is very less and loop area is small. Now, what is the hysteresis loop for soft magnetic materials? Let us see. Loop area is small. That means the hysteresis loop is like this. Small. It is slim. H and B. In this case of hard magnetic materials, the hysteresis loop area is large. Hysteresis loop area is large, like this. Okay. Here, soft and hard magnetic materials means loss of energy in case of soft magnetic materials is small. Loss of energy is small. Here, loss of energy is large. Loss of energy is large. Hysteresis loop area is small. Area is small. But here, area of the loop is large. Area of loop is large. Now, what about coercive field and residual flux density in case of both soft and hard magnetic materials? In case of soft magnetic materials, they are small. They means residual flux density and coercive field both are small. Are small. But in case of hard magnetic materials, residual flux density and coercive field both are large. Residual flux density and coercive field are large. So what are the advantages, applications of soft and hard magnetic materials? Because of small magnetic residual flux density and coercive field, these soft magnetic materials can easily magnetized and demagnetized. That means for low applied magnetic fields, it acquires a saturation state. For low applied reverse magnetic field, the residual flux density becomes 0. That means the soft magnetic materials are easily magnetized and easily demagnetized. Easily magnetized and easily demagnetized. But here, what about the values of Br and Hc? They are large. So, to become a saturation state of a ferromagnetic material, one has to apply a large amount of applied magnetic field. That means it is very hard. It is very hard to magnetize hard magnetic materials. But here the coercive field is also large. So we need to apply a large amount of applied magnetic field so that the residual flux density becomes 0. So they are hard, difficult to magnetize and demagnetize. It is hard to magnetize and magnetize and demagnetize. Now, so what is the application for this easily magnetized and demagnetized? They can be used in alternating mechanical circuits. So, high frequency alternating mechanical circuits, we can use soft magnetic materials. Alternating high frequency mechanical and electrical circuits. But here hard magnetic materials, we can use the hard magnetic materials in case of preparing permanent magnets and toys like that. Permanent magnets. Permanent magnets. So here soft magnetic materials are also used in transformer cores, alternating transformer cores. Alternating current case, we have to use step down and step up transformers. In that case, there is a core in the transformer. That core material is made by soft magnetic materials. Transformer cores. So this is about soft and hard magnetic materials in case of ferromagnetism. Thanks for listening this lecture.